follow-up of Wojtek's talk. But instead of investigating the regret, I will investigate some new estimator, which we call regret, not regret, but fitting indicator. So I explain immediately. So I'm not going to talk about how to predict your choice on TV. I will just talk about how to detect cats in pictures. But basically, it's the same principle. You have your machine receive a lot of pictures of cats, or with or without cats, and yes, of course, it has some moment to compare with the situation where there is no cat. And for some, and you give, when you train the machine, and then say how the machine is doing the magic, and just the principle, you provide picture and label. So the feature are picture, and label is a binary label. Here we say cat when there's a cat, no cat when there is no cat. Say 1 when there is a cat, and -1 when there is no cat. Here there is some ambiguity, but because we have both. So when you do that, you have a machine. So this is a machine. It's more complicated than that, but you know, I cannot, I don't understand everything. So the machine, like what explained, contains a class of models, a set L of models. And the models basically map a sequence of labels with feature. And each model gives a probability that for such picture, you have the probability to have the label Y. And the functions are very simple. So the objective for the machine is to, when you enter all the picture and all the label, to find the model that fits the best the sequence of pictures. So capital T is a training set, XT is a sequence of the feature, of the which are picture in our case, and YT is a label sequence. Very important comment that has been done, that you don't know what is the probability of for given feature to have a label Y. In fact, if you are considering cat, you know when a picture contains cat and doesn't contain cat, but you are not capable to write the probability as a function of the pixel of the picture, of the Fourier transform of the pixel of the picture. You are not capable to do that. People try that for several years, how to detect a cat with a formula, and they never succeeded. So it was a mystery. Our brain can do that, but a machine could not do that until recently. There are several learning strategies. The learning strategy that, which is a strategy that we all prefer, is a maximum likelihood, that you have a sequence of pictures and you want to know the model that will give you the label with the highest probability. So it is something which is I will say, normal to consider. Sometimes it is not possible because of the picture. To train a machine, you need millions of pictures. You need millions of cats. So sometimes it is impossible to compute the maximum likelihood. Then you use, if the set of models is a vector space, you use an incremental strategy with a gradient descent. The neural networks, the deep neural network are using a strategy of incrementation. But it is done like that because it is too complex to make the matrix of 1 million by 1 million of all the picture and to find the maximum likelihood. But in fact, the purpose is to simulate in some way a maximum likelihood. And of course, when you define, you select a model, you have a loss. The loss has this expression. It is a loss for one picture. Basically, it is a logarithm of the probability. It should be the minus, in fact. There is a typo, it should be the minus of the logarithm. And when you do the expectation, you find the loss that was described by Wojtek. Here, there are many cats, as you can imagine. This is a picture you can, if you submit to your machine the same picture, the same cat, at the end, this machine will be only capable to detect this very cat. And if you give another cat, the yellow one, it won't be, how can snooze can my cat, but okay, this has nothing to do with our discussion. Therefore, your machine won't be capable to detect cat in other situations than this situation, cat in the snow. So when you test with such new cat, it will just say, oh, no, this is not a cat. This is something else, I don't know. So this will, so it will fail. This is very bad. It is called the overfitting. What you submit to the machine doesn't have enough diversity. So it is training again and again on the same cat. And so it is not capable to imagine. If you have too much diversity in your training set, you have underfitting. What is underfitting? You submit a lot of picture and you don't have enough picture. They are too different. And then the machine won't be capable to not have enough training to really detect there is a cat in the picture. Here, if I give you only these 3 pictures, and then give you this picture, it will say, oh, this looks like this one. And no, this is not a cat. In fact, it is a car Christine in the famous movie that only old-timer remember. And this has also impact in another side of machine learning. It's called generative artificial intelligence. I don't understand very well it is. What I understood, just you make training, and at the end, you ask the machine to generate a casual random cat. In this case, it will judge, this machine will generate only this cat. So it is not really interesting. As if you want to, as if ChatGPT is a generative artificial intelligence, as if ChatGPT will always produce the same text. In underfitting, same thing, it will produce any garbage and say, this is a cat. If you want the machine to generate a random cat, it will generate a random bullshit. So this is to see if training is overfitting or underfitting is an important issue in machine learning. And what I want to show you is the fact that you can basically give a mathematical model about overfitting and underfitting. The mathematical model is more complicated, but in our case, is basically L of theta t is the model you select after the training. If the model gives you a probability that's larger than the actual probability of the nature, then you have overfitting. It means that there is not enough room to add a new picture with a different cat. All the probability weight is on this sequence. In underfitting, it means that the probability model you select at the end is in fact smaller than the actual probability of the source, of the nature. And in this case, it means that you still have more room, you still have room to add to this weight, to add bullshit, so that the machine can detect a cat where there is no cat. So what is interesting, this case, we can really give a mathematical expression of what is overfitting and underfitting. The fitting index. The fitting index, you can see, it's very simple. It is the ratio of the logarithm. If it is negative, we are in overfitting. If it is positive, we are in underfitting. Yes, it should be the contrary, but there are some historical reasons for that. What is interesting is the average fitting index. You can compute the average fitting index and charge this expression, nothing special. And we have overfitting if it is negative and underfitting if it is positive. Here, there are very simple theorem that if you hope that when your class of models contains the model of nature, the class of the model of the source. But in this case, you won't find the real, the exact model. You will find something else which will look closer to the sequence you submitted. But we will see that it's not, it is not so far. But anyhow, it is overfitting if the learning, if the source model is in the learning class. In the case, we are in the maximum likelihood strategy. Of course, if the strategy is just picked up at random, there is no such result, of course. So if you are in the maximum likelihood strategy, so something which is above the incremental strategies, you got this. It is very simple. The proof is just the fact that this is the maximum of all learning models of this quantity, and therefore you have, of course, this bond. This is very simple. Here it is a less obvious bond that we always, if we have overfitting, whatever the strategy, then the overfitting cannot be lower or larger than the logarithm of the Starkov sum. That was explained. So it's another way to find the utility of the Starkov sum. It is the maximum overfitting you can have. I think they are very close as concept. Now we are going to look at the specific class. The class of the logistic regression is interesting because it is the first class of machine learning. They are very old. They were used in the 50s, 40s or 50s. They are very old because they are computationally easy to use. And basically, you have a collection of points. Here, I take the case where you have a collection of points in the plan. And you can assume you have a collection point in the cube or in dimension, a large dimension. And you try to find a hyperplan that can split the set of positive labels with the set with a negative label. Of course, it is not 100% sure, so you have some mismatches. But you find it. Here is the case when you have basically the weight of the logistic regression is very large. It's 100. So in this case, you have a real split by the hyperplan. Here you have the weight is 5, 5. It's a vector. So it says the split is not absolutely perfect. So it is the real life. You may have picture which contain cat. In fact, it's not a cat because there is a bad shade in the picture, and there is some mistake. It is classic, normal. There are two theorems. But since it's an ongoing work, it is you can say theorem or conjecture, depends if we are confident in the proof or not. First, a theorem with logistic and if the source model is a logistic distribution, and we are in maximum likelihood strategy, then the fitting index, the average fitting index, is finite, and in fact can compute its value. In fact, to be finite, you have to remember that the fitting index is distributed over all possible labels, feature. For one feature, for one picture, the probability, the overfitting is 1 over t. So it converges quickly. But it's not zero. The fitting is not zero. Fitting zero will mean that it is exactly the model. And the counterpart of the theorem that when the source model is not in the set of models. For example, the set of models are all logistic functions bounded by some R. Then you have underfitting, and the underfitting index is increasing with t. It is a linear. Of course, you might always a non-zero error at each feature, at each training set, at each feature. Therefore, when you add all the error you do, at the end you have something which is linear. Here is a simulation, and the simulation, the interval shows a 95 percentile error interval, so it fits with the theory. Here it's how much time do I have? 15 minutes? Oh, it's too much. It's way too much. Okay. So basically, because Voltec explained everything, so I have no joke. The picture was the beginning. No, nothing. So, no, it will last 15 minutes. I already gained 2 minutes. So, and you have the coffee break earlier. This is a max finding lemma. I was not capable, we are not capable to give a name to this lemma. So there are two reasons. Maybe it is not very interesting, or maybe it is wrong. Both are possible. But I wanted to give a name with imaginary mathematician, Wilbur, because it is the first name of the first guy who fly in a plane in America. But no, I'm going to invent a name. So basically, this is the expression how to find the maximum of a function when you have the only tool you have is a Fourier transform. What the Fourier transform, we'll see later. So it has this expression, which is not very interesting because it's very complicated. it's the most complicated way to compute the maximum wave function. And the proof is very rather simple. That basically, it is attained at some W star, and this W star is necessarily the root of the gradient. We assume that the function is concave, convex. I always forget. No, this maximum, so it is concave. And you just express f of W if this it is a Fourier transform of this function. Don't ask me, it's too complicated. And that's basically, if I took the reverse, I will get at 0, I will get just the value of W star, which cancel this gradient. So that's all. Here you have this expression. And no, this is ugly. And when you want to obtain this expression, you have just to make a change of. So you are looking for f of 0. You have to make a change of variable. A is the gradient of f. Or the gradient of f. If you do the change of variable, you come to this expression. Sorry?
Is the lemma true if f is identical to 1?
Sorry? What is true?
Is the lemma true if f is just equal to 1 everywhere?
If where f is equal to 1 everywhere, what is the problem? Yes, why not? The determinant will be 0. So it may not be true. See, f is constant. This is kind of case where there is no a single root of this. So it can't work. We need that the root at least is unique. If the root is not unique, it won't work. But thank you, you gave me 2 minutes. We forget what it is. Yes. The fitting index, the average of fitting index, if it's just average of this means that you should know this function, but you don't need to know it. You have the picture and you average. Here, this you know. If you want to have really the average of fitting index, you have to know the entropy of your training set. And the entropy you can have in a clever way. I mean, not by taking all the picture and making the probability of each picture and the logarithm of the probability and some. No, you have some clever way to compute the entropy of something which is very large. When there will have never the case when there are two pictures which are identical. So it is not an issue. So if you want to compute this simply, this is the max. You have just to make the sum on all possible yt, sequence yt, of the function we have before, which is this function. For x yt, you have to add the maximum obtained by this expression. So this is this function. This is basically the sum of this function, but here, you cannot see it. Why you cannot see it? Because I didn't show it. All this all the YT is basically the sequence of -1 + 1 -1 + 1. So basically, it has some algebraic property when you sum everything. As I omit this algebraic property just to tell that you are capable to make this sum. This sum has this simple expression. Simple means you have to be, I would say, indulgent with the word simple in this case, where this has a closed form, but not complicated. Basically, it is a sum. It is a sum, but of size t. And this is a product form. And we use the fact that the determinant doesn't depend on yt. So we can put it in factor, but it is possible to have the determinant to depend on yt, but this is simple. And then you have this product. And this product, you have a big T element. Now, the reason why this one is of order T is because this is a sum of T element. And this will call to, if everything is correct, to a saddle point method. Because this is exponential of something of order T. This is of order T. This is something of T to power T, D, sorry. So we have something which is where you can apply in theory the saddle point method. Now here, just to relax a little the atmosphere, 6 minutes, I give you the W star dispersion when you select a sequence at random, assuming it is the source model that I give as a first example. Not the model with the cats, because it's more complicated. And you see that you have certain dispersion, and this is a real source model. Every time you are escaping from the source model, you have a fitting index which gets larger. Here it is when you limit the weight to 2. So the W star, the argument of the maximum, are just concentrated. So it's less dispersion, but the problem is they are more concentrated, but too bad they are not enough close to the real source model, and therefore this will incur an error, which will tend to be linear. Here it incurs an error, which is paradoxical. It's a fact that it incurs an error, but in fact everything is summed up, and you got only a finite fitting index. So it looks a big disorder, but in fact it's the consequence of that is every time you are wrong. But sometimes you are wrong, good wrong, sometimes you are bad wrong. Now this slide, I could spend 1 hour on this because there is a typo on every line. So I prefer not to. So let's see. The main error, there are so many errors, is here. It should be a minus. This is how to see how this function can behave like a quadratic function with some error. It could be a cubic here. And in fact, this function is like a quadratic, but it is non-positive. Even when you put the -1 here, why it is non-positive? Because it's not even real. There is a I, which is imaginary. But apparently, there is in the classification saddle point method, there is this case. There's a survey by Fedoruk, exactly, you investigate all this case, and there is a saddle point method. The saddle point apply even when the quadratic is not the kind of quadratic we have with the saddle point method. And you can detect that the determinant of this quadratic form is exactly the determinant of the Laplacian. So so you can apply the saddle point method if we believe in this. Now, if you ask Maple for this kind of integral, it is happy. You just write the answer. So for Maple, it's a classic saddle point method. So you must believe Maple. You may not believe me, but you must believe Maple. And then the story is very simple. The saddle point method tell you that basically the leading term is this quantity at W0, 0, and with an error of 1/t. The leading factor is nothing else than the entropy of the source. Then you get what you were looking for, the fact that the fitting index is not in 1/t because the entropy is order t, but it's finite. Good. Here is the expression of this constant, because it behaves like constant. It's complicated. You can. Here there is a special case with underfitting analysis, where in the case where the W0, the model index, is deterministic. So it just produces one splittable sequence. And you have this expression for the fitting index, which is pi2/6 times SD, which is the area, the volume of the sphere, with an error of order 1/r². Here, yes, this is important. Just in time, by the way. This is a reference. And of course, this beautiful book, I advertise also this beautiful book with the chief editor Wojtek here. And this is about the chapter 6, the limit of artificial intelligence imposed by information theory.
Thank you very much.